Okay, next topic in this chapter, chapter 2 on derivatives, is we're going to talk about, again, one interpretation of what the partial means. We're going to talk about that we can take partials of R4 and higher functions, and that we can take something called second partials. Okay, so let's get to it. First one, find all first partials of this function. So this is an example we want to start with. First of all, what type of function is this? Where does it live? What kind of space? So 1, 2, 3 independent variables affecting a fourth, so it lives in R4. So how many first partials? 1, 2, 3. So we'll get all first partials. A couple ways of writing this. You can write w sub x, and that's the same thing as f sub x. But that's also the same as, you might see d dx of that function sometimes, or sometimes you see del x, the Greek symbol, of the function with respect to the variable. So lots of different ways of saying the same thing. They all just say get the partial with respect to x of this function. So again, x is the variable, everything else is a constant. So I don't even care about that last term. It's just focusing on the first term. Well, I have a couple constants times 2x. So I'll have 2x y cubed z. Take a partial with respect to y. And so with the last term, we'll have something plus a z. And then here we'll do a power rule on the y cubed. So we'll get 3y squared times the x squared times the z. Doesn't matter what order you write those, so I just like to put them in alphabetical, but lots of ways of writing that. F sub z, the last first partial. With respect to z, we'll just get x squared y cubed plus y. Okay, so we learned some new notation. We learned that we can take partials of higher dimensional functions, and we can also do something called second partials. Okay, so in this case, we can compute the second partials. And this is just like a second derivative. So over here, for this, back in R2, this function again, we could take the second derivative. That was 6x. We could evaluate it at a point if we wanted and get 6. And that had a meaning. Instead of a rate of change or a slope of a tangent line, now this had something to do with concavity, right? And then it was concave up at x equals 1. So those ideas are going to extend when we take our second derivatives here, they're second partials. But there's lots of ways of doing second partials. So rather than doing a R4 function, we're actually going to go back to a simpler one, because there's going to be quite a few second partials. And when we go to R4, that it really expands it even more. You'll see what I mean in a moment. So let's take a slightly easier one here. Let me pause this while I clean the board for you. Okay, so I put a new function here, and we want to get the second partials. That's our new idea. Figure out how to compute them, and then what it's going to mean for us. And so let's look at this function. First of all, where does it live? It's an R3 function. So this is one we could visualize. Would never ask you to do this one by hand. Even with contour map, we would go straight to a tech tool for this one. So we know there's a surface out there, something visual, but we're not even getting that far yet. We just want to know how to crank away on these partials. The only way to get the second partials is through the first partials, just like over here, right? The only way to get the second derivative is through the first derivative. So let me go ahead and get my first partials real quick. There's only 2 of them, so no problem. 3x squared y squared plus 7 minus 2y. Again, you can pause the video and check it yourself. Do it for a moment. We're going to do f sub y if you want to pause and try that yourself. I'll just go ahead and do it here live. So we'll have 2x cubed y minus 2x. Okay, partial with respect to y. Now, second partials. So I can go back to each one of these and take another partial. So I can do an f sub x with respect to x, or I could do an f sub x with respect to y. Okay. And again, think about them in order, like xx, go to x and take the derivative with respect to x. This one says go to x and take the derivative with respect to y. And then I do the same thing for f sub y. So I go to y and I take the derivative with respect to x. and then I go to y, and take the derivative with respect to y. So in total, I have 4 second partials. F sub xx, f sub xy, f sub yx, f sub yy. And it turns out that they will almost always, for these problems, nice polynomial ones, the ones that you're going to see in your calculus life, are going to be such that these two are always equal. These are what are called your mixed partials. These are your pure partials. So your mixed partials, unless you have an ill-behaved graduate level math class, you're always going to see that these mixed partials are equal. That's one way to check your work, because you can take partial each way and see that they do match. Okay, so let's do our second partials. F sub x, x. Go back to f sub x, take another crank away again, but with respect to x. So with respect to x, I'm going to get a 6xy squared, zeros and zeros. Now I want to go f sub xy. That says go back to f sub x, that's the first thing, and take the partial with respect to y this time. So I'll have a power rule in the y squared, so I'll get 6x squared y with respect to y minus 2. Okay, now the partials, second partial is starting with y, so f sub yx. But again, it should be the same thing here. So let's just check this. So I go to f sub y, look at this line, take the derivative with respect to x. So I'll have 3 times 2 is 6x squared y minus 2. Yeah, they match. Good, that makes sense. It means I've done at least those parts, right? F sub yy, go to f sub y, take a derivative again with respect to y. So I'm going to get 2x cubed. That's it, minus 0. So for that previous R4 example, it'd be a good thing to check yourself, write it down. How many second partials would that have? Would it have 6, 8, 9, 12? Think about it. And would any of those be equal? Okay, I think that's a concept question at the end of the chapter, so you can check the answers there on that one. Okay, so summary, we can take first partials. We can take first partials and second partials. We can take them of R3, R4, and higher dimensional functions. We can evaluate any of those at a particular point. We didn't do that here, but it should be clear that you could get f sub xx at any point you want. Let's say at the point 1, 2. So that would be 6 times 1 times 2 squared, which is 24. And again, that has a meaning. Right over here, we talked about rates of change and concavity. We'll have something very similar over here with second derivatives when you evaluate those. Okay, let me see if there's any other comments on this section. Oh yeah, and we also talked about alternative notations. Okay, one last thing. What does it mean when I plug in at the point to the first partial? Let's do that same point 1, 2. So I'll have 3 times 1 times 4 is 12, plus 7 minus 4, which is 3, 15. Right, so I have this statement. I want to focus on that. What is f sub x at the point 1, 2 is 15? What does that mean? Okay, and this is what we're going to call the marginal effect. So the first partial, when you evaluate it at the point, gives you something called the marginal effect. So if this function z was a function of x and y, and let's say that margins usually have to do with business applications. So let's just say z is money, we're making bank, right? And x and y are 2 products we're making. Let's say we're doing a bakery and we're making like cookies and donuts, let's say. Okay, so we can interpret this. If there's some explicit function, I mean, I just made this up, so I'm sure that's not exactly the function for making cookies and donuts, and we don't really have a bakery, unfortunately. So if this is the case, what f sub x at 1, 2 means in terms of this particular function, it says you made 1 cookie, you made 2 donuts. But if you were to increase x, because you're doing a partial with respect to x and you treated x like a variable so it can vary, it can go from 1 to 2 to if you increase the number of cookies you make by 1. So that's your marginal effect. It's just a tiny little bit. You increase the number of cookies you're going to make by 1. How much more Z, how much more dollars do you make? What's the effect on Z? In this case, it's saying it's a positive 15. So these must be gourmet deluxe cookies. So if you make 1 more cookie, you go from making 1 to 2, but you keep the number of donuts constant at 2. Because remember how you computed that partial. You computed the partial with respect to x by treating x like the variable and y like a constant. So I'm going to keep y constant at its value of 2. So there's a phrase that goes with any function, any scenario, you know, bakery or otherwise, that you can say when x increases by 1 unit, in this case, from x equals 1 to x equals 2, and y is held constant, in this case, at y equals 2. So 1 cookie to 2 cookies, y held constant at 2 donuts. Then z increases, because z is positive, by about 15 units. All right, it wasn't the case, but let's just modify this and say, had we plugged in and got a big negative, we didn't, but just go with us here. What would change in this marginal effect statement? So x is still your variable, it still started at 1, it went up to 2. Y is still your constant, it was held constant at 2. Z, instead of increasing, would decrease by about 15 units. So this is how it's used in business. Again, this marginal interpretation of a partial. It's easy to compute a partial, evaluate it at a point, and see what happens. All right, so back to our business example with the bakery. What if I wanted to know, well, what happens if I start making more donuts? Is that going to be good for me or bad for me? Because maybe the cost of like the supplies for the donuts is more expensive or something. So you're not clear right away from this. So in this case, you would evaluate the partial with respect to y at whatever point you're interested in. Again, maybe we're not just making 1 and 2, we're doing hundreds and I don't know, 50, let's say, right? So you would find out, you'd plug it in here. We're not going to do that because that's a little bit bigger math right on the fly here, but 2 times 100 cubed times 50 minus 2 times 50, you get a number, it spits out a number here, and then you can interpret that number. That would say, because you're doing a partial with respect to y, x was held constant. So you say when x is held constant at 100 cookies, but donuts goes from 50 to 51, we'd expect to see about this much increase or decrease, depending on the sign, in the z value, which in this case was our money profit made. Okay, so again, summary, marginal effect, the last piece of this lesson that we want to make sure we understand what a partial derivative is actually doing for us. Our first partials give us marginal effects.